Hello there! In this portion of the linear algebra series, we're going to take a look at geometry and calculation of eigenvalues and eigenvectors. And I always like to make the connection between geometry and the calculation because some sort of visual will always help us make better sense of what's going on and navigate those floods. So, first of all, one observation that we've been able to make is that when we repeatedly multiply x by a matrix, so let's just say we're dealing with a 2 by 1 vector x, and we multiply it by a matrix A, which will be 2 by 2 in size, that this leads to some systematic transformations. So we will jump to this applet, and this applet is actually available in the video description, so that if you'd like to go experiment with it, you can, and you can change the A matrix itself. But let's say that we start off with a vector 1, 0. And there's our vector 1, 0 right there, lies along the x-axis, and then we have a matrix A, and if we take A times x, and then we multiply that by A, and then we multiply that by A, and that by A, and that by A, we're performing a series of geometric transformations on this vector. Now in 3 dimensions, the same sort of analogy applies. 4, 5, 6 dimensions, we can only think about it conceptually. So let's actually visualize this through the use of the applet. So here is that 1, 0 vector. Now right now, the red vector represents the transformation of the original 1, 0 vector. The black one is actually the 1, 0 vector. So right now what we're doing is we're raising a to a power, and since we're raising it to the 0 power, we're basically just returning the original vector back. Now if I increase that to 1, what I've done now is I've taken a to the first power and multiplied it by x. So basically x has been multiplied by one copy of a. Alright, one thing I'm going to do here is I'm going to right click this and choose show trace. That way we can trace and keep track of the tip of the vector and where it's been. And now when I multiply by a again, so basically a squared times x, I notice that once again that small red vector got transformed into that longer red vector. And something interesting has happened here. The black vector that was originally 1, 0 has sort of rotated, and it became this vector here, which I'll back up. That vector, well, that's not going to do anything now, but it became this shorter vector, and then when I multiplied it by a again, it became that longer vector. But the interesting fact is that it appears that after this first rotation occurred, the vector just seems to be growing in length. In fact, if I continue exponentiating this, you don't even see the vector moving at all. Its tip is somewhere up here, and that tip is getting higher and higher as a result of it. So let me back up here for a second. I'll kind of shimmy this out, and I'm going to zoom out, and so that we can keep track of that red vector. So we know that they're both down here at 1, 0. So if I choose t equals 1, t equals 2, t equals 3, t equals 4, and so on, and I keep doing this, I'm going to see that every time, right, that vector gets multiplied by some factor. So this gets scaled up to this point, which gets scaled up to this point, which gets scaled up even further. Now, one interesting thing that we can observe here is that if we keep track of the ratio of our current vector, so a to the 0 times x right now is just the vector 1, 0. And if I keep track of the ratio of y to x, I should notice that that ratio is going to become consistent, right? Because now I get the vector, which is the vector 1, 2, and the ratio of the y to x is 2 to 1. So I have a slope of 2 to 1 on that red vector. If I extend it one more time, again, 10 to 5, a slope of 2, 50 to 25, a slope of 2, 1250 to 625, 6250 to 3125, and so on. Now, what that must mean is that if the slope is staying the same or becomes consistent, then that must mean that also the vector corresponding to this guy, when I multiply it by some constant scalar, I'm going to be getting this guy here. So I'm going to keep track of this multiplier, and what this will do is I start off on the vector 1, 0, and then when I multiply by a one time, I get the vector 1, 2. Now the factor is not here evident, it's showing infinity because I have a 0 and I'm getting a divide by 0 error, but now when I look at the difference between one multiplication by a and two multiplications by a, I see that the vector will go from 1, 2 to 5, 10 if I increase t by one more. Well, that we can see is a jump by a factor of 5 from 1 to 5. The same factor from 2 to 10 is a factor of 5. And so basically, every time I multiply by one more copy of A, I multiply each of the two components by 5. We see that here again. And I do it again, and I do it again, and I do it again, and the multiplier is 5. So this vector here is 5 times this vector. This vector here is 5 times this vector. And that continues on indefinitely. If I change these values, so let me change this matrix. Let's pick 0. Let's do this. I'll have to reset this whole graphic here. So let's say I have 0, and maybe we'll put in a 1.2 here, and then maybe we'll put in a 0.6 there, and maybe we'll just go ahead and leave that one the same. Okay, so now what I should notice is, once again, some change. Actually, let me make this one 0.8. Okay, I should once again notice that right now, nothing's really happening here, but as I begin increasing t, I notice that black vector just became that red vector. So it went from a vector of 1, 0 to the vector 0, 0.6. Okay, and right now I see that if I multiply by A again, I'll get the vector 0.72, 0.48, and there's a factor of 0.8 that's been applied to get from one to the other. So let's see, let's do this again. And check it out. It once again appears that I'm ultimately, the ultimate fate of this vector as it gets repeatedly multiplied by A is such that it was kind of wobbling around here for a little while, for a few iterations, for a few multiplications by A, but then it became, again, stable in one direction, and the vectors simply got scaled. Now, raising A to the 13th power and multiplying it by X gives me that vector right there. Multiplying it by X by A to the 14th gives me that vector right there, and I see a common ratio of 1.34. That means a factor of 1.34 applied to that gives me that. 1.34 applied to that gives me that. If I do it again, I'll probably start to see that the slope is pretty consistent and the multiplier is also pretty consistent. And I see a slope of 1.12 and a factor of 1.34. The initial vector that I pick is also not relevant. So if I made this 1, 4 instead, and I continued multiplying, again, I'd probably get a little bit of variation, but check it out. In the long run, we're on a ratio of 1.12 to 1, meaning that the slope of that ultimate vector is going to be 1.12, and the multiplier from one vector to the next, well, since we're traveling along a straight line, the only thing that changes from here to here is that this guy gets scaled up to a vector that looks like this. So let's jump back and do a little bit of analysis. So we're going to formulate an observation. We're going to say that for large enough t, a to the t times x is approximately some vector v. Okay? Well, so what have I done here? Well, I've just told you, let's give it a new name. We're going to call it v. Where when I multiply that vector by a, I get some constant multiple of that vector. So what we're trying to illustrate is exactly what we saw in that applet. If I started with a vector here and I scaled it, maybe it jumped up here, but then maybe it jumped over here, maybe it jumped back here, then maybe it jumped over here, and it started to vary a little bit less, and then eventually it just sort of started traveling up along this straight line. So right around here somewhere, I see that x has been basically, x vector has been scaled by a large enough power to approximately become this vector v, that every time I now multiply by a, all that's happening to that vector v is that it's getting scaled by this factor that we're going to call lambda. Now that factor called lambda is called an eigenvalue, and the vector itself is called the eigenvector. And this guy is called its corresponding eigenvector. Okay, value vector makes sense. Now, how do we find these lambda? How do we figure out this long-run behavior? Well, we see that for large enough powers applied to a, when it multiplies into x, we see that this behavior persists. AV equals lambda v. Now, what I'm going to do is I'm going to isolate the vector v, and I'm going to do that by moving lambda v to the left, and then I'm going to right factor v. But remember that A is a 2 by 2 matrix and lambda is a scalar. So I can't subtract a scalar from a matrix, so I make it lambda I, because I is the identity matrix, and I can insert the identity matrix pretty much anywhere I want, right? I can say that that's really lambda times I times V, because it's the same thing as saying lambda V. Okay, well now I'm going to make an observation. In this equation, if I just think about this as some black box matrix right here, then that matrix multiplied by a vector equals 0, the 0 vector. The vector V equals 0, 0 will always work, right? Because regardless of what this matrix is, when I have 0 components for V and I multiply them both into that matrix, I'll get the 0 vector. I don't want that, right? I want other solutions. So the way I'm going to ensure that I get more than just the 0 solution, well, let's see. A system will either have 0, 1, or infinitely many solutions. Therefore, if I want more than just one, I'm going to require infinitely many solutions. So the way I'm going to find lambda is I'm going to say, well, this matrix then better be singular. So I want this to be singular. What does that mean? It means that the determinant is equal to 0. Okay, so I'm going to force the determinant of that to be equal to 0. I'm going to set the determinant of a minus lambda I equal to 0. I'm going to find a lambda that's going to guarantee me more than just the 0 vector. And for each lambda, we're going to find the corresponding v with Gaussian elimination. So here we have the matrix 1, 2, 2, 4 that we're focusing on. A minus lambda I is the first thing we compute. There's our A matrix. Lambda times I is just going to scale the two ones by lambda, take their difference. We get 1 minus lambda 2, 2, 4 minus lambda. Now we take the determinant of that and set it equal to 0. Well, what's the determinant? The determinant is the product of the diagonals minus the product of those diagonals. 1 minus lambda times 4 minus lambda minus 2 times 2, set equal to 0. And so when we distribute that all out, we get a quadratic polynomial. Now, a quadratic polynomial is going to have two roots. So there are going to be two eigenvalues. And guess what? A 3 by 3 matrix is going to end up having a determinant that has lambda cubed in it, and it will have 3 roots. Those could be real, imaginary, complex, any combination. So, but the important part is that there will always be as many eigenvalues as the dimensionality of that square matrix. Okay, so I can solve this using graphical technology, and I can find where this parabola crosses the x-axis, and where it does that is at lambda 1 equals 5 or lambda 2 equals 0. Okay, now I need to compute the eigenvectors. All right, so the way I'm going to do this is, once again, now I'm going to recompute a minus lambda I, but I know that lambda 1 is going to be 5, and I'm going to start solving for v1. So if I do that, 1 minus 5, 4 minus 5, that changes these two diagonals. I get this matrix times v1. Now v1 just contains components, x and y, and the 0 vector is just equals 0, 0. So I'm going to form the Gaussian matrix, 4, 2, 0, 2, negative 1, 0. I get 1, negative 1 half, 0, 0, 0, 0 when I do the reduced row echelon form version, and that obviously means that since I have a 1 pivot here, that means I'm going to, x is going to be deterministic, but because I don't have a pivot for y, then that means y is going to be a free variable, and I'm going to assign y some arbitrary value of c, right? Because y could be whatever I want, and once you tell me the value of y, I know that x is going to equal 1 half c. So x equals 1 half y. The second equation is irrelevant. It's not going to give us any information. And I'm just going to pick c equals 2, because then I don't have to deal with fractions. And I can say that, all right, well, if c is 2, that means my y value is 2. My x is 1 half of that, which is 1. And I get an eigenvector. Okay, so here we have it. Lambda 1 equals 5. v1 equals the vector 1, 2. We can see that once x gets multiplied by enough copies of a, it moves in the direction of v1, right? It stayed on that slope of 2 to 1. 2 to 1. And each additional copy causes it to grow by a factor of 5. That's the beauty of this. This explains why we saw the behavior that we did. Similar process for the second lambda. We subtract 0, so that doesn't change the matrix at all. We do the reduced row echelon form version. Again, y is the free variable. We assign y equals c. I'm going to go ahead and pick c equals 1 because that's easy to work with. And I get v2 is the vector negative 2, 1. Summary. Lambda 1 equals 0. v2 equals negative 2, 1. So the question is, why does this vector not indicate the ultimate direction or the fate of x? Well, the fate of x when multiplied by a to the t is determined by the eigenvalue with largest magnitude.